The third type of calorimetry problems are mixtures. It's when two different substances or the same substance at different temperatures are added together. When one is at a higher temperature than the other, the higher temperature will give off heat, and the heat that is given off will be absorbed by the cold substance until they reach thermal equilibrium. Thermal equilibrium means that the rate of exchange is going to be equal and they will become the same temperature. So the general formula for mixtures when one is added to another, meaning that one starts at a higher temperature and one's at a lower temperature, is Q hot equals to Q cold. In general, the easiest problems will have two equations, one in the hot side and one on the cold side, but these problems can have more than two equations. We know that the hot object must release heat. Since it's releasing heat, the hot is always going to be exothermic. The cold object or substance must absorb that. It's going to be endothermic. Exothermic objects release heat, so they have a negative value. Endothermic objects absorb heat, so it is positive in value. The simplest equation for Q hot and Q cold is mc delta T of the hot is going to equal to mc delta T of the cold. If I rewrite my temperature, which is mc T final minus T initial, this is my hot. My cold is also going to be mc. I expand the delta T, T final minus T initial, and this is my cold. Since the hot is at a higher temperature initially, we know that the T final is going to be a lower temperature. If the T final is at a lower temperature than the T initial, when I do the delta T, the value is going to come out negative. But for the cold, we know the final temperature is going to be higher than the initial temperature. The cold is going to get warmer as it absorbs the heat that is released by the hot object. So when I figure out delta T, it's going to be positive in value. So in math, a negative cannot equal a positive. To correct for this, what we do is we put a negative sign in front of Q hot to make it a positive value to equal to the positive value of Q cold. So if I stick a negative value in front here and I expand this out, this is going to be negative mc T final minus T initial. For the hot, the cold is still going to be mc T final minus T initial. So I need to distribute the sign, which is negative mc T final minus a negative times a negative is a positive mc T initial. So if I rearrange this, this is going to be mc T initial minus mc T final. This is still going to equal to mc delta T of the cold side. If I factor out mc, this is T initial minus T final. This is for the hot side. And my cold side stays as is. So to make the problem easier, when we have Q hot equals to Q cold, we know we need to put a negative sign in front of Q hot to account for the negative to make Q hot positive. To make it easier, so instead of sticking the negative sign in front, when you write the hot side, whatever object is hot, flip the temperature make it T initial minus T final for the hot side. And for the cold side, it is going to stay as final minus initial. This is my cold side. And this right here will account for the negative sign. If you choose to write a T final minus T initial, make sure you distribute the negative to both the TF and the T naught. Let's look at this first problem. If 20 grams of silver are mixed with water, so we have two different substances. We have silver that is mixed with water. So we know this is going to be a Q hot equals to Q cold. So I'm going to identify silver has a mass of 20 grams. It is at 350 degrees Celsius, so that's my T initial. My water has a mass of 200 grams. This is at an initial temperature of 30 degrees Celsius. They want the final temperature, so we are looking for the final temperature. And since it's going to reach thermal equilibrium, the final temperature has to be the same. That means we know the C of silver, which you could look up at your table, which is 0.240 joules per gram degrees Celsius. C of water, we know this is at liquid state because it's at 30 degrees Celsius, which is 4.186 joules per gram degrees Celsius. So we know this is going to be a Q hot equals to Q cold. We know the hot is going to be silver because silver starts at a higher temperature than water. So Q cold is going to be my water. So this is going to be MC delta T of silver equals to MC delta T of the water. The mass of silver is 20 grams. My constant is 0.240 joules per gram degrees Celsius. Since silver is my hot, we're not going to use T final minus T initial. We're going to flip our temperature so we could account for the negative sign. So this is going to be 350 minus T final. This is equal to the mass of the water, which is 200 grams. The constant, which is 4.186 joules per gram degrees Celsius. T final is what we're looking for, minus 30 degrees Celsius. Now we're going to calculate. So we need to multiply this first and then distribute. So if you multiply 20 times 0.24 times 350, you're going to get a positive 1680 minus 20 times 0.24 times a minus T final. So that's going to be 4.8 T final. We're going to do the same thing on the opposite side. 200 times 4.186. Then we're going to distribute to TF. So that's going to equal to 836.8 TF. We're going to multiply 200 times 4.186 times 30. And that's going to be approximately 25,104. Now I'm going to simplify. I'm going to get all the TFs to one side. Since this 4.8 is subtracted, I'm going to do the opposite. Add 4.8 T final to both sides. So that cancels out. I'm going to move my 25,104 to the opposite side by adding to get rid of it. Now I'm going to clean it up a little. I'm going to add 1680 to 25,104 to get 26,784. On the opposite side, I'm going to add these two numbers, 841.6 TF. I'm going to divide both sides by 841.6. So TF is approximately 31.825. So T final is going to be approximately 32 degrees Celsius. Pause the video, solve this problem, and then check your answer. This problem is also a Q hot equals Q cold. We have two different substances here, sodium chloride and mercury. So they're mixed together. That's your clue that is a Q hot equals Q cold. One starts at a higher temperature, one starts at a lower temperature. So the first thing we're going to do is identify the variables. So for NaCl, we have a mass of 24 at an initial temperature of 25 degrees Celsius. We are looking for the T final here. It says find the T final. And they gave you C of NaCl above. So now I'm going to identify the variables for mercury. So mercury, we have a mass of 272 grams. Its T initial is 50 degrees Celsius. So that tells you mercury is your hot and your sodium chloride is your cold. T final we don't know, and they gave you the C. So this is going to be, again, Q hot equals Q cold. I'm just going to write Q cold equals Q hot because I identified the cold first. Equation is still MC delta T, and this is for the NaCl. This is going to be MC delta T of mercury. The mass of sodium chloride is 24 grams. Its C is given as 0.864 joules per gram degrees Celsius. Since it is cold, it's going to be T final minus T initial. I'm just going to write exactly like it is. This is T final minus T initial, which was 25 degrees Celsius. On the opposite side, the mercury's mass is 272 grams. Its C was given as 0.14 joules per gram degrees Celsius. Since this is the hot, my temperature is going to be T initial minus T final. My T initial was 50 degrees Celsius minus T final. So now I'm going to do the math here. So we're going to multiply 24 times 0.864 and then distribute to TF and then to the 25. So when I do that, this becomes 20.736 T final minus 518.41. I'm going to do the same thing on the opposite side. I'm going to multiply 272 times 0.14 and then I'm going to distribute it to the 50 and the T final. This is going to equal to 1,904 minus 38.08 T final. Now I'm going to move all the TFs to one side and the rest to the opposite side. And if you do your math correctly, you get T final with approximately 41.18 degrees Celsius. Pause the video, try this problem on your own, and then check your answer. In this problem too, this is a Q hot equals Q cold because we have ice at 0 degrees Celsius placed in a glass beaker containing water. Even though they're both made up of H2O, one is at a lower temperature, the other one is at a higher temperature. So this is also Q hot equals Q cold. And the other clue is, what is the final temperature of the mixture? So the first thing I'm going to do is I'm going to identify variables. So we have ice as one of my mixtures. The mass of ice is 50 grams. It is at 0 degrees ice. So if you don't know where 0 degrees ice is, I'm going to sketch the heating cooling curve. So 0 degrees ice is right here. This is where it's melting and freezing. It's at this point. Since we have a final temperature and the ice is at a lower temperature, we know the ice is going to melt. In order for our ice to melt, we have to go towards the right by adding more potential energy and heat energy. To melt ice, this is a phase change, so we need the latent heat of fusion, which is equal to 333.6 joules per gram. The ice started at 0 degrees Celsius, which is located at this position. It melted and became 0 degrees Celsius water. Since we are looking for a final temperature, the final temperature is not 0. That means there's enough heat given off by the warm water to raise the temperature of the initial ice. When the ice moves up after it melts, it is no longer in the solid state. It is in the liquid state. So for the ice, there will be two equations. It has to melt and then it's going to be warmer water. So if I write my equation, Q cold equals to Q hot. The cold is my ice. My hot is my water. Based on our sketch, there are two equations for the ice. The first one is MHF plus MC delta T. This is when the ice is now in the liquid state. Since it's in the liquid state between 0 and 100, I need to use C of water, which is 4.186 joules per gram degrees Celsius. The water has a mass of 400 grams. It has an initial temperature of 50 degrees Celsius, and we are looking for the final temperature for both. Since it's in the liquid state, we know C of liquid is going to be 4.186 joules per gram degrees Celsius. So the equation for the hot is MC delta T, and this is the warm water. Now I'm going to rewrite the equation below and plug in my numbers. So this is going to be MHF plus MC delta T, and this was for the ice initially. On the opposite side is going to be MC delta T of the water. So my mass of the ice is going to be 50 grams. My HF is going to be 333.6 joules per gram. Plus my ice mass is still 50. The C, after it melts, is no longer a solid state. It's at the liquid state. So the C I will use is 4.186 joules per gram degrees Celsius. Since ice is cold, my delta T is still T final minus T initial. My final temperature, I don't know, we're looking for that, minus the initial temperature. When the ice melts, we are at 0 degrees. So my initial temperature is 0 degrees Celsius. This is equal to the mass of the water, which is 400 grams. It is still, the constant of water is 4.186 joules per gram degrees Celsius. Since water is hot, our T final minus T initial becomes T initial minus T final to account for the negative sign. Our T initial was at 50 degrees Celsius minus T final. Now I'm going to simplify the math. So the first thing I need to do is multiply 50 times 333.6. That becomes 16,680. Do the MC delta T, so 50 times 4.186. And we're going to distribute to T final, and 0. 0 doesn't matter because it's going to come out 0. So this becomes 209.3 T final. This is equal to the opposite side. So we're going to multiply 400 times 4.186. And then we're going to distribute it to the 50 and the T final. So when we do that, we get 83,720 minus 1,674.4 T final. Now we're going to move all the T finals to one side, and we're going to move all the numbers to the opposite side. And when you do that, you should get 1,883.7 T final is equal to 67,040. And so if you divide both sides by 1,883.7, T final is approximately 35.589 degrees Celsius. Pause the video, solve this problem, and then check your answer. This problem 2 is a Q hot equals Q cold. Because we have plastic, which is substance 1, it is placed in water, which is substance 2. And we're looking for the heat capacity of the plastic. So I'm going to identify the variables. So for the plastic, we have a mass of 40 grams. It is suspended in boiling water, 100 degrees Celsius. So that tells you that the initial temperature of the plastic is 100 degrees Celsius. After it was placed in the boiling water, it was removed from the boiling water and placed in another water that has a mass of 200 grams with the initial temperature of 15 degrees Celsius. If the temperature of the water increased to 20, that is my final temperature of water, that means the plastic must also have a final temperature of 20, because this is a Q hot, Q cold. All the heat released by the plastic needs to be absorbed by the water until they reach thermal equilibrium. And we're looking for the C of the plastic. We know the C of the water is 4.186 joules per gram degrees Celsius. So this is a Q hot equals to Q cold, in which the hot is plastic and the cold is water. This is MC delta T of the plastic equals to MC delta T of the water. I'm going to start plugging in. The mass of the plastic is 40 grams. The C of the plastic, we don't know. We're looking for that. Since the plastic has a higher initial temperature, we know delta T has to be switched to account for the sign. So T initial minus T final. T initial is 100 grams. T initial is 100 degrees Celsius. My T final we know is 20 degrees Celsius. This is equal to the cold. The mass of the water is 200. The C of the water is 0.186 joules per gram degrees Celsius. My T, since this is the cold, it's going to remain as final minus initial. My final was 20 degrees Celsius minus 15 degrees Celsius. We're going to simplify the right side. First, we're going to do the work in the parentheses, so 20 minus 15. Then we're going to multiply by 200 and 4.186 and give 4,186. On the opposite side, we are going to do the parentheses work first. So 100 minus 20 is 80 times 40 will give you 3,200 C. And we're going to divide both sides by 3,200. And C is going to equal to 1.308 joules per gram degrees Celsius. This is number 41 from your packet. We already solved this in class together. Try it again. Pause the video, solve it, and then check your answer. This problem is also a Q hot, Q cold. In this case, we have three substances. We have aluminum, we have ice, and we have water. We are looking for the final temperature. So I'm going to identify my aluminum has a mass of 45.8 grams. My initial temperature of aluminum is negative 5.2 degrees Celsius. We're looking for the final temperature, and the C you're going to get from your table that I provided is 0.9 joules per gram degrees Celsius. My second substance is ice. My mass is given as 45 grams. My initial temperature is equal to 0 degrees Celsius. Ice. So I'm going to sketch the heating cooling curve. So if I look at that, this is 0 degrees Celsius. This is where the phase change occurs. Right here is 0 degrees Celsius ice. Since we want to have a final temperature and ice is going to be a cold, since ice is Q cold because the water has a higher temperature, we know the ice is going to melt. Since the ice is going to melt, we need the heat of fusion. So we have HF, which is 333.6 joules per gram. In addition, we know there's going to be a final temperature, so my ice is going to melt. My ice is going to melt, and then it's going to be heated up. Since we are at the diagonal, a constant for water, which is going to be 4.186 joules per gram degrees Celsius. Then we have water. The mass of the water is 2,000 grams. My T initial is 95 degrees Celsius. My T final, I don't know. Since it's still in the liquid state, CH2O is going to be 4.186 joules per gram degrees Celsius. So my equation is going to be Q cold equals to Q hot. The aluminum and the ice are cold. Why? Because it's at a lower temperature than water. The water will lose the heat that the aluminum and the ice will gain. So the equation for aluminum is going to be MC delta T, aluminum. But for the ice, is going to be MHF because it needs to melt, plus MC delta T because we're going to take the melted 0 degrees water to a higher temperature. And on the opposite side, we're going to have MC delta T of the hot water. Now I'm going to start plugging in numbers. So my aluminum is 45.8 grams times the C, which is 0.900. joules per gram degrees Celsius. My T final, I don't know, minus a minus 5.2 degrees Celsius. A minus and a minus is a plus. And since this is the code sign, we leave it as T final minus T initial plus MHF. So the mass of the ice is 45 grams. Latent heat of fusion is 336.6 joules per gram plus ice becoming warmed up. My mass is still ice being warmed up. The mass is still 45 grams. The constant now is 4.186 because it is at 0. It melted and it became 0 degrees water, and now we're heating up that water, so we're in the liquid state. Since this is the cold one, this is still T final minus T initial. T final is what we're looking for, minus T initial, which is 0 degrees Celsius. This is equal to the hot side. The mass is 2,000 grams. Since it's liquid, it's going to be 4.186 joules per gram degrees Celsius. Since this is the hot side, my T final minus T initial must be flipped to T initial minus T final to account for the sign. So this is going to be 95 degrees Celsius minus T final. Now I'm going to simplify, and we're going to start here, 45.8 times 0.9, and then we're going to distribute it to the T final and the positive 5.2. So that's going to become 41.22 T final plus 214.344 plus 45 times 333.6, 15,012. We're going to multiply 45 times 4.186 and distribute it to the TF and the 0, but you already know anything times 0 is 0. And so this is 188.37 T final. This is equal to the right side, 2,000 times 4.186. You're going to multiply it to the 95 and distribute it to the T final. 795,340 minus 8,372 T final. So now I'm going to put all the T finals on one side. I'm going to move them all to the left to make it positive. So we have a T final here and a T final here on the left side, and on the right side we have a negative T final. So I'm going to add 8,372 to both sides. So if I do that, I'm going to get approximately 800. I'm going to get 8,601.59 T final. Since I moved all the T finals to the left side, I need to move 214.344 and 15,012 to the right side. So these two numbers here are going to be, it's going to be subtracted from 795,340. So this becomes, so you can divide both sides by 8,601.59. So T final is going to be approximately 90.69 degrees Celsius. When you have two or more substances at different temperature, it is going to be a Q hot and Q cold. To account for the negative sign for the temperature change, it is easier if you make the hot side T initial minus T final.